Okay, I'm going to get started again. So the last thing in the first half of section 9.1 is talking about these things that are called initial value problems. So if you remember, what I've talked about so far is the idea about the differential equation being an equation that has a derivative in it. And different functions can be solutions to that equation. You can have families of solutions. Now, oftentimes, again, differential equations represent how a quantity changes over time. It talks about how the rate of change of that quantity is related to the value of that quantity. Now, if we actually knew where something started, we should be able to predict where it's going to go over time. So the idea is, if we knew where something started, we should only be able to get one solution to the differential equation, rather than a whole family of solutions. And it turns out that yes, that is the case. If we know what the starting value of the dependent variables, we know what y starts at, we will actually know what y is going to be over the entire length of time. That should only give you one solution to the differential equation. That starting value, that thing you need to get started, is called an initial condition. It's sort of a piece of information you know about what's going on, which allows you to solve the differential equation in question. The combination of a differential equation and an initial condition is what's called an initial value problem. So the word initial value problem means differential equation plus initial condition. Again, usually a differential equation has infinitely many solutions. It has a family of solutions. An initial value problem has only one solution. And if you know what the initial condition is, you can use the value. You can find the value of any of those constant, those c's that are floating around in a family of solutions. So example 3 here, we have functions that look like this. Y equals ln x plus c over x. Right? And we want to show that every function in this family is a solution to that differential equation. X squared, y prime, plus xy equals 1. Right, to show that every one of these functions is a solution to this equation. By the way, for those who, I'm actually just going to, before I even show that part, I'm just going to even talk about what the family of functions represents. Because I think that thinking about families of functions is sometimes difficult for people. When I'm talking about a family of functions, just think about it as a bunch of different graphs. So one of them could be ln x over x. Oh, I have to do brackets here. Right? That's one of them. I could also have ln x plus 1 over x. That's another one. I could have ln x plus 2. I'll do 3. That's another one. I could have ln x plus 2.1 over x. Oh, let me get rid of that times. And the idea is each of those curves that this graphing calculator has come up with, this one, this one, this one, and this one, they're all different solutions to that differential equation. What they mean is they're basically all different situations which obey the law of physics that the differential equation represents. And the idea is, depending upon where you start, you're going to follow a different one of those paths. So if you start here, you're going to follow this path. If you start here, you're going to follow this path. If you start somewhere in here, you're going to follow a path that goes through somewhere in there. The idea is each of those paths sort of represents a situation that you can follow that follows this. Again, differential equations you can sort of think of as laws of physics, or they're not all physics. Sometimes some of them are chemistry, some of them are biology stuff, but they're all sort of a model which describes how things change over time. So what we want to do is we want to show that all of those curves, they're all solutions to this differential equation. So what we've got to do is we've got to take the derivative, y prime, and we'll multiply by x squared, add xy, see if we get 1. Well, if we take the derivative, we're going to have to use the quotient rule. The derivative of the top is 1 over x. The derivative of anything plus c is 0. Times the bottom, which is x, minus the derivative of the bottom, which is 1, times the top, which is ln x plus c, all over x squared. So if I have x squared y prime, Well, x squared multiplied by y prime is just going to cancel off that x squared on the bottom. 1 over x times x is 1. So x squared y prime is 1 minus ln x minus c. X times y, well, if this is y, we multiply it by x, it'll cancel out the x. So x times y is ln x plus c. Now, if I take 1 minus ln x minus c plus ln x plus c, that does give me 1. So this function is a solution to the differential equation. We oftentimes use the word DE to represent differential equation because it takes a lot of space to write that all out. So again, we can check this thing as a solution to that differential equation by taking its derivative and plugging it in. The second part of example 3 asks us to find a solution which satisfies the initial condition that when you plug in 1, you get 2. So the initial condition here is y of 1 equals 2. That means when x is 1, y is 2. And that should tell you which of those different lines we're on. Right, so if you look back at these graphs, right, when x is 1, y is 2. That means we're up here somewhere where I put my cursor. So basically, we're probably going to be on a curve that looks very similar to this one up here. So for part B, we know when x is 1, y is 2. So I'm going to look at this equation for the solution, and I put 2 in for y, and I put 1 in for x. So I get 2 equals ln 1 plus c over 1. Ln of 1 is 0, so 2 equals c over 1. So c equals 2. Right? So the constant is 2 in this situation. So the solution is this. Ln x plus 2 over x. This is a solution to that differential equation which satisfies the condition that y of 1 equals 2. Now, for part C, we could do the same thing. Rather than saying that y of 1 equals 2, I said y of 2 equals 1. That's basically saying that when x is 2, y is 1. Right? So again, use the same formula for y in terms of x. Put 1 in for y, put 2 in for x. Multiply both sides by 2. 2 equals ln 2 plus c. Subtract ln 2. 2 minus ln 2 equals c. So the solution is y equals ln x plus 2 minus ln 2 over x. This is the solution to this differential equation that satisfies this condition. Okay. Any questions about this example? Okay. So the last thing in section 9.1 that I'm going to talk about is the idea of visualizing differential equations. What does a differential equation say about a graph? Right? I said, if you look at my, again, back to foo plot, I said that each of these curves is a solution to the same differential equation. The question is, how can we relate a curve to a solution? All right, that's basically what I'm asking. I'm asking, well, how can you visualize the solutions? What is the graph going to look like? Now, one thing we can say is we can say where is the function going to be increasing and where the function is going to be decreasing. We can say that by just looking at the differential equation. Because the differential equation is really a statement about the slope of something. If you want to know where it's going to be increasing, where it's going to be decreasing, you're asking basically where is it positive, where is it negative. So, sometimes a differential equation, when it's like y prime equals some formula involving x and y, sometimes that formula can be factored. If it can be factored, then we can predict whether the derivative is going to be positive or negative. If you can predict whether the derivative is positive or negative, you can predict whether the function is going to be increasing or decreasing. So if one of the factors is 0, if you factor it out and one of those things is 0, then, if it's 0 for a certain y value, c, so if it was like y minus 3, it's 0 and y is 3, then f of x equals 3 is what's called an equilibrium solution or constant solution. It's a solution which neither increases nor decreases. It stays put. Some differential equations do have equilibrium solutions. Equilibrium solutions, again, physically sort of represent balancing points. If there's an even number of negative factors, so if it's like x minus 2 times x minus 3 and x is 1, negative times negative gives you a positive answer. So the solution will be increasing. If there's an odd number of negative factors, the solution will be decreasing. And we can use these ideas to sort of study differential equations, say, okay, where is it going to be increasing, where is it going to be decreasing? Where's the solution going to be increasing, where's the solution going to be decreasing? So for an example of this, we've got a function which satisfies that differential equation there. So the function is, or the differential equation, sorry, is dy dt is y to the fourth minus 6y cubed plus 5y squared. So the idea is this thing can be factored. We can factor out a y squared. We're left with y squared minus 6y plus 5. And then this thing here we'll factor as y minus 5, y minus 1. So if we ask what are the constant solutions are also known as equilibrium solutions. There's solutions where the slope is 0. The solutions that are not changing. Well, for the solution to not be changing, either this has to be 0, this has to be 0, or this has to be 0. So y equals 0 is one constant solution. Y equals 5 is another. Right? Y equals 5 is the thing that makes that second factor 0. And y equals 1 is the last one. The one that makes that third factor 0. So those are the constant solutions. Y equals 0, y equals 5, y equals 1. Next, they want to ask for which values of y is y increasing. Well, the idea is what I can do is I can think about the y-axis. Sorry. And we know we've got an equilibrium solution here. We've got an equilibrium solution at 1. We've got an equilibrium solution at 5. And the question is, if y is between 0 and 1, is it increasing or is it decreasing? Well, if y is between 0 and 1, we could try y equals 1 half. So in that case, the derivative is going to be y squared, which is a quarter. A half minus 5 is negative 4.5. A half minus 1 is negative 0.5. That thing results in a positive number. Positive times negative gives you a positive result. So if y is a half, if we're in here, it's going to be increasing. The slope is going to be moving upwards. So if we have a solution between 0 and 1, that solution might look like that green one there. If we picked, let's say, y equals 2, something between 1 and 5, then the derivative would be y squared, which is 4, y minus 5, which is negative 3, y minus 1, which is 1. That product gives you something negative. So here we're going to get decreasing solutions. For y values between 1 and 5, we're going to get solutions which are negative, which are decreasing. We could have a solution that looks like that. Would be an example of something that would fit in that value. Pick something bigger than 5. Let's say y equals 6. Then the derivative is y squared, which is 36. Y minus 5 is 1. Y minus 1 is 5. That's a positive thing. So if we're up here, our solutions are increasing. And if we're down here at like y equals negative 1, then the derivative is y squared, which is 1. y minus 5, which is negative 6, y minus 1, which is negative 2. This gives you a positive result. So down there, we're also increasing. So for which values of y is y increasing? Y is increasing if y is in the interval from negative infinity to 0, or the interval from 0 to 1, or the interval from 5 to infinity. It's increasing here, here, and here.
Is this where the idea of direction fields comes from?
Yes, this is exactly where the idea of direction fields is like slopes, and putting the slopes on the graph and trying to sketch slopes from that. Now if you want to ask when it's decreasing, it's going to be decreasing exactly the opposite place. Here's where it's going to be decreasing. Yes, Dylan?
Wouldn't you just be able to put it's increasing from negative infinity to 1 and then 5 to infinity?
At 0, it's not actually increasing. At 0, the slope is 0.
Oh.
And that's why I sort of tried to draw that blue line. That blue line was supposed to be that equilibrium solution where the slope is 0. So if it's a little bit below 0, it's not going to be increasing. If it's a little bit above 0, it's going to be increasing. If it's actually on 0, it's not going to be increasing. So y is decreasing if y is in the interval from 1 to 5. The marker I was using. Okay. Any other questions about this example? Okay. The last thing I'm going to talk about is how you can look at a solution visually, and see if it, makes sense with the graph that you're working with. So if you want to figure out what a solution should be increasing or decreasing, right? Doing that sort of analysis that I did in that, where I had that equation, right? Seeing when, factoring it, seeing when it should be positive, when it should be negative. I can look at a graph and say, does that graph look reasonable? Right? If I had a graph that looked like this, that's not a reasonable solution to that differential equation. Why? Because it's increasing up here. It should not be increasing up here. It should only, it's increasing down here, and it should be decreasing down here. Right? It should be decreasing, it's increasing, it's clearly not an actual solution. So we can use these sorts of ideas to examine graphs. So example 5, we have a graph from the textbook on page 585. The graph looks like that. Wait, am I looking at the right one? Yes. There's the graph. And so the question now is this graph a solution to A, B, or C? Right? Which of those differential equations is the graph a solution to? Well, one way of doing that is sort of looking at different points in the graph and comparing what the slope is and what the coordinates are. So here, we have a situation where x is 0, right? X is 0 and the slope is positive. Right, at that point in the graph, the x-coordinate is 0 and the slope is positive. If we look at the first equation, if we plug in x equals 0, we get y prime equals 1 plus 0. Great, it could be this one, right? Because when x is 0, the slope is positive. If we look at the second equation, and we plug in x equals 0, we get y prime equals negative 0. It can't be that equation, because when this equation, when x is 0, the slope is not positive. Or could it be C? Here we have y prime equals 1 minus 2 times 0, which is 1. Okay, so it could be either of these. They both give us positive slope when x is 0. Okay, so that might not be enough for us to figure this out. Let's look here. Right at that point on the graph, we have x is approximately 1, y is approximately, now annoyingly the scale, actually, let me just write it this way. X is positive, y is positive, and the slope is 0. Right? We don't even know what, again, this, if you actually look at your textbook on this page, they don't actually tell you a scale on the x and the y axis. But we can tell at this point that both the x and y coordinates are positive, and the slope is 0. Now the question is then, which of those two equations that we have left actually fit that information? Well, the first equation says that y prime equals 1 plus xy. If x is positive and y is positive, we get y prime is 1 plus some positive number. There's no way that can be 0, right? So it cannot be equation A. So now if we look at equation C, and we have y prime equals 1 minus 2xy, here we have y prime is 1 minus some positive number. That could be 0, right? So it must be equation C. Equation C is the only one that fits the data we have. Okay.
Can you explain why the first line couldn't be again?
Because here, when x is 0, oh, like this one?
Yeah, that one.
So at this point in the graph, x is positive, y is positive, the slope is 0. In this equation, if x is positive and y is positive, the slope is 1 plus a positive number. 1 plus a positive number can never be 0. Yeah. Annoyingly, and this is something I wish, this is one of the reasons I make videos of these things. Oh, my hair stuck in there. One of the reasons I make videos of these classes is because there's most of the thought that goes on in these sorts of questions is difficult stuff for me to write down without writing out full sentences that would take me a lot more time than I have in the classroom. So one of the things I do sort of try to write some of them on the slides itself, but the other reason I'm making these videos is so that if you don't sort of understand the actual thought that goes into it, if you just look at the equations, you're like, I have no idea what you actually did with the equations, go back and look at the videos on YouTube. And you'll actually hear the thoughts that go into it because I'm saying that out loud. Math actually has two different modes of communication that are part of it. There's the actual doing the math, writing out the equations, and there's the explaining what you're doing when you're writing out the equations. And most teachers, myself included, write out the equations using writing and explain what I'm doing using words. When you're actually writing a math paper, usually you actually write out both of them. If you've ever seen like my written solutions to stuff, you'll see I have all these paragraphs in there. That's because I'm explaining what I'm doing when I'm doing it. And that's how I write math papers too. When I would like, yeah. But the idea is that oftentimes I don't write all that when I'm writing things on the board. And the reason is because writing full sentences on the board takes up a lot of time. I put some of them on slides, and other ones are going to come out orally. So the spoken part of what I'm doing is just as important as the written part. Yeah. Especially for questions like this, where I haven't really been writing that much. I've sort of been explaining what I'm doing. And this is one of the annoying things about these sorts of problems is marking them becomes harder because you don't write as much when you're doing them. Most of it's happening sort of in the reasoning part of your brain. It's harder to express in written form, but yeah. Okay, so I'm at the end of section 9.1. We have 20 minutes left in class. And I have two options for what I can do with the 20 minutes. I can skip the group problems for today's class and go barreling ahead and start covering section 9.3. In some ways, that's preferable because it means you'll have more of the material to study over the weekend if you want to help get ready for the test. The second option is I can give you the group problem and you can work on it and we can go over the solution. Now, if I give you the group problem, I want folks to actually stay and work on it. There's been a lot of classes recently where I've given folks group problems and they've just gone home. And I don't think people have actually been doing it at home. I know some people have, but I think the majority of the class has not. So basically what I want to know is whether or not you prefer to stay and work on the group problem, or whether you prefer to stay and have me start the next section. I'm going to take a class vote on this. But either way, I want you to stay till class is actually over at 1:40. It's just a question of what you want to do while you're staying. So how many people would prefer to stay and work on the group problem? How many? Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. How many? 10? Okay, how many people would prefer to stay and work and start the next section? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to start the next section. This means I will push back the group problem that's going to be for today till next class, and we will have a chance to work on it in the next class. But yeah, I mean, my preference is for starting the next section too, because it's the very next thing I'm going to cover is sort of a key idea, which is important in dealing with anything in 9.3 or 9.4. So skipping section 9.2. Section 9.2 talks about how do you solve a differential equation using basically a graphing calculator type approach. You know, you do things like you draw these little slopes on your graph and you sketch a curve that goes through the slopes. I am not going to cover that. Part of the reason is because those sorts of questions are ones that don't give you exact answers. So it's hard for me to mark those questions. They're not really any good WebAssign questions on those sorts of things. And also partly because I don't think it's as important as the actual techniques of solving differential equations. So section 9.3 is actually about solving differential equations. How do you come up with solutions to differential equations? And there's one specific situation I'm going to talk about, and that's the situation of what are called separable equations. So again, when you're solving a differential equation, what you're trying to find all solutions to an equation. Let's find all the solutions to this differential equation. Has anyone here? Oh, yes.
Sorry, I was just wondering if there was a handout.
Oh, thank you. Yeah. You're right, I have used up everything that was on the last handout. Okay. So yeah, section 9.3, what we're doing things is we are finding all solutions to differential equations. Like, find all the solutions to that guy there. Has anyone here solved separable differential equations before? Remember separation of variables? Okay, I see one hand. Yeah. It turns out to involve integration. So you'll have more practice doing integrals when you work on these problems. They will usually be simple integrals. They will usually not involve anything more complicated than substitution or integration by parts. You won't see any trig substitution, you won't see any partial fractions. Or if you do see partial fractions, I'll do the partial fractions part for you. You know, like those sorts of things. So the first thing I'm going to mention is some differential equations we've actually solved already. We have solved differential equations that look like this. Y prime equals 2x. Right? This is an antiderivative problem. Right? The solution to that differential equation is y equals x squared plus c. So you've actually already solved some differential equations way back at the beginning of this course when we talked about antiderivatives. When we have y prime equals something which only has x's in it, solving the differential equation is the same thing as doing an antiderivative. So what we're going to try to do is we're going to try to take any differential equation we have and try to turn it into differential equations which can be solved using antiderivatives. Solving things using antiderivatives is always a lot easier than solving many other methods. So the goal is to try to take something and make it into something we can do antiderivatives to. Now, the reason that this we can solve using antiderivatives is because here there's only x's. There's no y's on the right-hand side. That's what makes this solvable using antiderivatives. So if we have other sorts of differential equations, our goal is always going to be to try to get all the x's on the right-hand side, all the y's on the left-hand side. So no y's on the right, no x's on the left. So to see an example of this, I'm going to do y prime equals e to the x y squared. So one thing we can do is we want to move all the x's to the right, all the y's to the left. We divide both sides by y squared. Now, one way of writing this, y prime is dy over dx. So we can write it as dy over dx equals e to the x. And one of the things that's annoying about this formula is there's a dx here on the y side. So let's multiply both sides by dx and see what happens. We get that dy over y squared is e to the x dx. So here we have all the y's on the left, all the y's on the right. This looks, again, this is like one of those substitution formulas where du equals something times dx. dy and dx, again, are these sort of weird things that represent a small change in y and a small change in x in there. Understanding what they actually are is sometimes difficult. But what we have here is an equation that relates something with a dy and a y in it to something with a dx and an x in it. Well, something with a dy and a y in it, that is something we can integrate. And something with a dx and the x in it is something we can integrate. And it turns out that if dy over y squared is e to the x dx, then the integral of dy over y squared is the same thing as the integral of e to the x dx. It's just the same thing as like if we had, x dx equals 2u du or something like that, right? The integral of x dx is the same thing as the integral of 2u du, right? So if we can get this equation out here, the integrals of both sides will give the same thing. And the idea is that these are both integrals we can easily do. We can do this integral as just y to the negative 2. We can do this integral as just e to the x. So our goal when we're separating variables is to get all the y's on the left, all the x's on the right, and integrate both sides. It's called separation of variables because we're separating the y's from the x's. So when we do separation of variables, when we solve separable equations, we're going to follow these 5 steps. The first step is to factor the right-hand side, so it's something that has only x's in it times something that has only y's in it. Usually that's going to be the easiest approach to separate those two things from each other, just to factor the right-hand side. Once you've factored it, divide both sides by a thing which only has y's in it. That'll move those y's to the other side. Multiply both sides by dx. That'll move the dx to the other side. Step 3 is to write an integral sign in front of both sides. Do this step. Step 4 is to integrate both sides. Now, again, in questions I've done before where there's been 2 different integrals, I haven't been writing 2 different plus c's. Only put one of the plus c's in. So usually I only put the plus c on the right-hand side. You can put it only on the left. And the last step is to solve for y. Because usually once we do that integral step, we'll have like y to the something power equals x to something else power, or something like that. When we want a solution to a differential equation, we want to solve that thing for y. What is y actually going to be? Yes, Dylan?
What do we do if we can't quite separate it, say if it's like sine xy or something like that?
Then you need other methods which will not be taught in this course. So the short, actually, yeah, the long answer is that solving differential equations is a field in which active research is being done. So there are differential equations out there that people still do not know how to solve, and we've been trying to solve for hundreds of years. Separable equations are one type of differential equation. They are the easiest ones to solve. Actually, no, second easiest. The easiest are these guys, the antiderivative ones. The second easiest are the separable ones. But solving them is still only a small part of solving all the differential equations that are out there. So I'm going to do 2 examples, and that'll be it for today's class. So the first example is this guy here. Y squared plus xy squared times y prime equals 1. So what I'm going to want to do is I'm going to want to factor this thing. Now if I could move this over to the other side, factor it, and then move something back. I'm not going to do that. I'm just going to factor it over here. Again, if you follow the steps rigidly, the first step says write y prime equals f of x times g of x. You have to move this over to the other side, then I have to move part of it back again. That's kind of pointless. So I'm going to factor out a y squared. I'm left with a 1 plus x times, and I'm going to write the y prime as dy over dx. And then I move all the x's to the right, all the y's to the left. So I have y squared dy equals dx over 1 plus x. The next step is to put an integral sign in front of both sides. If we integrate y squared, we will get y cubed over 3. If we integrate this one, we'll get ln of absolute value of 1 plus x. And usually we put this plus c on the end. So now if I want to finish solving, I'm going to multiply both sides by 3. Finish solving for y. So I'll have 3 ln absolute value 1 plus x plus 3c, and then take the cube root of both sides. Y is the cube root of 3 ln absolute value of 1 plus x plus 3c. So just to go over that again, I had that equation. I factored the left-hand side by taking out a y squared. Moved all the x's to the right, all the y's to the left. Put an integral sign in front of both sides. Integrate y squared, get y cubed over 3. Integrate 1 over 1 plus x, get ln absolute value of 1 plus x. Multiply both sides by 3, take the cube root of both sides. Yes?
Does that matter when we add the plus c? Because you said
Don't
that
wait till the last step to add the plus c. So if you did this, this would not be correct. Why?
So
if you do this, sorry, maybe that is not correct.
so for this situation we don't add the plus c at it until the last, right?
Yeah, you add the plus c when you finish the integration step.
Okay.
So the idea is, from here, you always have to add the plus c before you rearrange the equation. That's another way of putting it. Because when you rearrange the equation, you're actually moving the c around. And sometimes a c which was here is no longer going to be on the outside. Now it's inside a cube root symbol. And those, yeah. And it turns out, I don't have time to do this today, but if you checked this guy, you plugged into the original equation, it would not solve the original equation. Yes?
It wouldn't make any difference though if we did the C
After
bringing it right.
this step,
Yeah.
this step would not make a difference.
Okay.
Because-
I don't understand why we don't add it on the left.
Well, we don't add it here.
No, on the left of what?
Oh,
Yeah.
the reason, okay, the short answer is if I put a plus c and a plus c, those two c's will cancel once I start rearranging, and that means I've gotten rid of the plus c that should still be there. That's the short answer. The long answer is, or maybe this is another short answer. When I did things like I split something up into two separate integrals, I only ever added 1 plus c. The idea is that technically there should be 2 plus c's, but they sort of but this one would be like a plus c1, this one will be a plus c2.
So the one accounts for
And I
both of them?
combine them
Yeah.
together, I just say
Okay.
c equals c1 plus c2. So same thing here. There could be a c1 here, a c2 here. Move a c1 over. This c is really c2 minus c1.
Yeah, okay.
Is what that c really is. Yeah, they're all constants. It doesn't really matter what you call the constant. Same thing, some people will actually just write this as plus c rather than plus 3c here. Because 3 times a constant is still a constant. It's just it's not the same constant, but it's still a constant. So if you see in their solution plus 3c and your solution plus c, those are both the same solution. And I need to make sure that WebAssign knows this. I'm pretty sure it does. It seems with this textbook, it's usually pretty smart, but I just hope, yeah, it won't happen. So the second example I'm going to do, the last example I'm going to do for today's class in the 5 minutes that are left, which is actually the perfect amount of time, is this equation here that I want to solve. Now, one thing to mention about this equation, or it's in some separable equations, there are some separable equations out there where it's impossible to solve for y in terms of x. We can't actually rearrange it to get y equals something. So in that case, the best we can do is what's called an implicit solution. If you remember implicit differentiation from calculus 1, an implicit function is something where it's not solved for y in terms of x. It's just an equation that involves x and y, like x squared plus y squared equals 1. Some differential equations, that's what their solutions are going to look like. And that's okay. They're not as useful solutions, but they're still better than not having any solution at all. And I will tell you whether or not I want an implicit solution or an explicit solution on the test. Yeah. It won't be a mystery to you whether you have to solve for y in terms of x. Oh wait, this was example 1. This is example 2. So here we have dy over d theta is e to the y sine squared theta over y secant theta. So the idea is here the dependent variable is y, independent is theta, so we'll get all the y's to the left, all the thetas to the right. So I have y dy over e to the y equals sine squared theta over secant theta d theta. Next, put an integral sign on both sides. Now we're going to have to do a little bit of work to integrate both of those guys. For the left one, we have to recognize that an e to the y on the bottom is the same as an e to the negative y on the top. For the right-hand side, I have to recognize that a secant on the bottom is the same thing as a cosine on the top. Now for this one, I'm going to have to use integration by parts. So I'm going to pick u to be y, dv will be e to the negative y dy, so du is dy, v is negative e to the negative y. So left-hand side will integrate to negative y e to the negative y minus the integral of v du. Now for this side, for the right-hand side, I've got an odd power of cosine and an even power of sine, which means I'm going to use the substitution u equals sine theta. So du is cosine theta d theta. So this side becomes an integral of u squared du. So I'm going to have to finish over here. When I integrate the last part, negative e to the negative y is just e to the negative y. Integrating, I get negative e to the negative y. So the left-hand side will be this. Negative y e to the negative y minus e to the negative y. Integrate u squared. I get u cubed over 3. And then I just got to plug back in what u is. U is cos theta.
Sine.
Oh, u is sine. Why was I was looking at my du then. Thank you. There we go. So that's the final answer there. Negative y e to the negative y minus e to the negative y equals sine cubed theta over 3 plus c. Trying to solve this for y, I don't know if you can tell by looking at this equation, it's going to be very difficult. It's going to be impossible, actually. So that's where you would leave that one. So anyways, I will continue with section 9.3 next class. There will be a web-assign on this stuff for you to work on over the weekend. It'll just be on 9.1, it won't be on 9.3 stuff. Take a look at that. Start studying for the test. The practice test should be up tomorrow. So if you want to take a look at the practice test, it'll be ready pretty soon. Yeah. Otherwise, see you Tuesday. You still have a week and a half. No, I'm doing everything early, so yeah. I'm ahead of schedule. Well, I'm ahead of schedule with my prep work because I'm behind schedule with the actual class. Yeah. Yes.
When you're explaining the plus c, how it doesn't add up to you just choose a different constant. If you go like plus e, then wouldn't that be the same?
Okay, let me show you the difference. There is a. Okay, in that last example, I had this. Whoa, I never want this to find now. Something plus c. Right? That's not the same thing as this.
Well, if the constants are the same. If the constants
No, even if the constants.
Really?
Yeah. So let's say, I'm just thinking if I can give you a good example. Oh yeah. Here's a good example. Let's say the differential equation is y equals 1 over 2y.
Okay.
So that's a solution, right? Square root of x. Derivative of square root of x is 1 over 2 square root of x. Right? What about this? Take the derivative of that thing. It's going to be 1 derivative of x plus 1 times derivative of x plus 1, which is 1.
Okay.
Right? This works. What if I take this guy? What's the derivative of this? It's 1 over 2 square root of x.
But wouldn't the constant change then if it was outside?
Okay, let's make this a 2. Point is, no matter what number you put here, it will not be a solution. This guy is a solution. There is no way you can write this with a square root of x plus something else. Square root of x plus 1 is not a vertical translation of square root of x. It's not square, no matter what number you put here, this is not the same as this.
Okay, so I was thinking if you had a plus c outside, it would be a separate function of x.
Yeah, no, so
that's
you're
what I'm-
right if this was a function of x, but it's a constant, it has no x's, and that's the key thing. So you're right, you can put you can put
it down, at least you'll get some hard marks.
If I put like
If you put
c,
that
then
in,
c is actually equal.
C is this
Yeah,
yeah,
so,
but
that doesn't happen.
yeah, exactly, because it's a constant.
Alright.
That's the idea. Yeah.
Thank you.
You're welcome.
I have a bit of an annoying question. This
Yeah, yeah.
comes over from Calc 1 actually. Just because we're doing it more and more often is multiplying the dy's and dx's. I was told that you're not technically supposed to just think of it as multiplying like it's an algebraic thing.
Like
So why is
this,
the reason? Yeah,
so
why
like
are
as a derivative?
yeah? Like why are we just able to multiply the dx? Like I don't understand.
Okay, so the answer, yeah. So why are you able to? So the short answer is
Because like when we first learned about it, we were just told, that's one solid thing basically. But then all of a sudden we're able to move it. I don't understand why we're able to move it.
So one thing which they sometimes cover, so in Calculus 1, and they don't always, is that there is a meaning for this thing that's on it. There's a meaning.
Yes, and we did see that. See
Okay.
those meetings.
And the idea is that it turns out,
Wait, did you say then maybe two?
here, when they're on their own, I'm going to put boxes around them.
Okay.
It turns out that this equation is always true. That
Okay.
dy over dx is
Okay.
dy over dx.
Okay.
But to know what these are, you need to know what a derivative is to begin with.
Yeah.
To know what a differential is, you need to know what a derivative is.
Yes.
You don't
The
have to
differential is
so
just
that's-
the change on, you
Exactly.
take the slope, you take the line tangent, and
Yeah.
then
Yeah.
the differential is just the change from the line in the
Yeah.
actual function or whatever.
So this is basically the.
Yeah.
These are. It's an identity.
Okay.
This symbol is not the same symbol as the differential of y divided by the
Right.
differential of x,
But
but they
it's
are equal.
always
They're always
true.
equal.
Okay.
Yeah. So you can always replace one with the other, and
I see.
yeah, that's
Okay.
that's the answer. And the reason when they first introduced the derivatives, they say
Right.
dx, dy, dx have no meaning on their own because in order to actually know what a differential is, you have to know a derivative first.
Okay.
But
Okay. So yeah, it is, a derivative is really just by itself, but it also has an
Yeah.
identity which is separated into
Exactly.
the dy over dx.
Exactly.
Okay.
And historically speaking, this symbol didn't come about until after people had invented differentials.
Right, okay.
This symbol is the
Leibniz notation.
yeah, exactly. And well, I actually don't know what I guess Leibniz did. I actually have not read Leibniz's actual calculus,
Okay.
so I don't know exactly if he actually if he must have introduced. I'm not sure if he had another symbol for derivative before he introduced differentials. I think not though, because he believed in infinitesimals.
Okay.
So
Yeah.
there's two ways to think what differentials are. One is the idea of differentials being these infinitesimally small changes in
Yes.
y and x.
Yes.
And that's what, and that, as far as I know, was the point of view that Leibniz had.
Yeah.
And that's why he said, this is nothing wrong with writing this. It's actually dividing this infinitesimally small change by this infinitesimally
Right,
small change.
right, right.
Yeah.
I'm glad you explained that
Yeah.
because that was something that really frustrated me, and I'm not just. I hate it when I get
Yeah.
told that this is how it is, and there's no, just go with it kind of thing.
Yeah.
So
And
it's-
thank you for asking, because I know that.
I like to
things-
understand
Yeah,
what's going
exactly.
on, even some people might say, well, that's not going to really help you, but
No, but it certainly will if you take any future math courses.
yeah.
And I know that I've been noticing this recently, that my emphasis on teaching has become, I spent too long tutoring, I think is what it really comes down
Yeah.
to. And when you're tutoring students who want tutoring don't want to know this stuff for the most part.
Yes. Yeah,
That's
I
been-
know
that's
that
been my
too. I've
experience.
helped lots of
Yeah,
lots of
exactly.
people. Yeah.
And so I've gotten so used to just skipping it, and I'm
Okay.
realizing when I'm teaching this stuff, I need to not skip it. That like the concepts are
It's funny
actually
because
important.
if you can believe it or not, in grade 12, like I did terrible in math. Like,
Yeah.
I did absolutely terrible, and it's because I just never took the time to learn
Yeah.
what's really going
Yeah.
on.
Yeah.
And once you really know what's going on, it just seems to make so much more
Yeah.
sense. So
Yeah.
that's why I like to ask
Yeah.
questions.
And thank you for asking them because again, my notes are based. I haven't taught this course in 3 or 4 years, and most of those 3 or 4 years I was spending tutoring.
Yeah.
So like 2 of those 3 years I was tutoring full time. So basically, it means that my new notes that I'm making for this is totally based upon the way I teach it when I'm doing tutoring, which means I am skipping a lot of theoretical aspects.
Yeah.
And I'm realizing this like halfway through the course that next time I teach this course, I need to actually throw in more theory early on.
It is
So,
nice to get the
yeah.
theory, but also I completely know that the majority of people
Yeah.
don't want to see that for sure.
Yeah.
So I was just meaning to ask.
Yeah.
I didn't get the assignment or the quiz done this week. I was just held up with a new course, 2
Oh,
projects. and-
Like the web assigned quiz.
Web
you
assigned
did
quiz.
this quiz, right?
Yes, but
Okay,
I
good.
didn't do the web assigned quiz
Yes,
or
yeah.
the hand-in assignment. So
yeah.
I'm wondering what I can do about that.
Well, I can give you an extension. At this point, I'll have to take off. Like, unless you have. Well, it depends. I mean, if it's just. I mean, usually, like, it's like, if there's, like, something that's beyond your control, I will, like, just give you an extension, and usually otherwise I'll take off some percentage points for it. When do you think you can have it done by?
Sometime this weekend.
So this weekend? Okay.
Because I definitely want to work on it anyways to get practice for the
Yeah,
midterm.
yeah. So I'll probably. I was gonna say that's gonna be like. Oh. You know what? Part of the other thing is, my policy is for written assignments. I don't give extensions. I can't take any submissions after I've handed back the marked ones, because it means that the answers are out there, and you could ask someone who has a marked one. Now, I can probably, certainly, like in this case, I can be lenient about it. Like I don't think, I don't want to like prevent you from doing it entirely, but I will have to take some percent off, and I have to figure out probably 20%, I think.
Could you just give me like, could you change some of the variables around and give me a more difficult version or something?
For the written assignment, yes, I'll do that. I'll give you a more difficult written assignment.
Yeah, I appreciate it too because I need
Yeah,
to practice
exactly.
for the midterm.
And then I can, I'll totally do that. That's.
Thanks.
For the quiz, we'll just have to give you an extension and like take off 20%. But for the website quiz, because I can't, the question bank is, especially for these sections, is not nearly as extensive as I'd like it to be. So I can't really pick completely new questions from there. But, yeah.
All right. Thank you.
You're welcome.
See you next week.
See you.